Да, добрый день, уважаемые коллеги. Okay, so should I talk in English? Probably. Yeah, good afternoon. Ladies and gentlemen. So, my talk is devoted, as it follows from the title, to the modern trends in the LED technology. And here is the outline of my talk. It is planned that I will give a short introduction where I actually touch even some economical issues related to LED industry and solid-state lighting in general problem, but also we'll discuss some technical aspects, and in particular we will have some intermediate conclusion about necessity of so-called integrated solution. And then, step by step, I will explain what are challenges to achieve these integrated solutions, both scientific challenges and also technological challenges. To start, I discuss the market for LED industry. So nowadays, practically everybody can go in the store and buy such a lamp. This is LED lamp. So this is Optical production, and you will see at Optical what nowadays there happen. But also it is expected, how it is shown here, that approximately 2020, 70% of the whole lighting industry, lighting market, will be related to such solid-state lighting devices. And also it is expected that the main product will be such so-called retrofit bulbs, retrofit lamps, which have the so-called socket E27, and therefore can be easily used in all existing home and communal applications. And here is the estimate that nowadays total number of existing sockets is more than 20 billion. So it is a tremendous amount, and of course the money related to this market is also very big. Good. So in addition, we have, of course, the industry application, communal application, some special applications, and altogether it generated such a market in the millions as it was estimated a long time ago, but actually nowadays we follow these tendencies. This is LED components, which includes which are both in the luminaries of general application, for example, like this one. I believe that this is also already LED projector, and also in bulbs. But of course, if we consider the luminaries themselves, there is additional price for housing, electric component, and so on. I will discuss this also. What about Russian market? In Russia, of course, we have similar tendencies, but usually we have specific features. And not always we have the same in Russia that in the surrounding world. So this is somehow good in many sense. First, of course, because of the high price of such bulbs, not everybody family, not everybody consumer like to go to the store and buy this. And also, this is somehow restricted with rather low electricity price in Russia. Therefore, people still think that it is good enough to go with these incandescent lamps and also maybe these luminescent lamps and so on. But tendency still remains, and it is the same as in the world. And nowadays, we have such amount of market. Therefore, we expect, for example, but also I will touch this point a little bit later, that the price for the retrofit lamp, which is analog of the 60-watt lamps in 2015, will be about 300 rubles, which will be rather reasonable. But of course, the target, and we will see it also later, it is about $2 US or maybe like 60 rubles per such product. Okay, what happened with the parameters of this LED lighting devices? And of course, we know that the heart of this LED device is LED itself, so light emitting diode. And here I have a growth of the efficiency or efficacy, how it is called in this industry, of single diodes, LED diodes used for general lighting application. And we can see that starting from 15 lumens per watt, nowadays it is already 180 lumen per watt available, but of course for different quality of light. This works for so-called cool light, but if we like to have a warmer light, it is still efficacy is not big enough. And estimated tendency is given here. So nowadays we are approximately here. We still have a theoretical possibility to improve the quality, which is dictated by electronic and optoelectronic properties of materials, maybe approximately 50%. The other important, of course, parameter is the price. And here we have a tendency of diminishing this price. Starting with very high price, this is so-called $1 US per kilolumen. We have a clear tendency of decreasing. So now we have approximately maybe $10 per kilolumen, and target is $2 per kilolumen. From which parts all these economical things and all these predictions are formed? What is behind this? Of course, behind is the science and technology, nothing else. So here I give the example of the components and important physical phenomena and technological process used in production of the final product, which is the LED luminary. First, of course, it's necessary to start with the substrate or wafers. And this is actually the key component, and I will talk a little bit later about this in more detail. Then we have production of light-emitting heterostructure itself on the level of the chip production, and making of the geometry and contact structure for this LED chip. And this can be done exactly with the help of these lithography processes, what we have heard in the previous talk. Of course, next important stage is the packaging, when we add luminophores or phosphors to produce desirable color of light, desirable quality of light, because usually these chips are nowadays made to produce a blue light. After that, we don't like to use a single LED, but we like to have moduli. Therefore, we need to form these modulus, add electric drivers, so have the electric sources inside. At the next stage, we make a luminary itself using housing. This housing, of course, we'll use in addition to, say, aim of mechanical stability. Of course, different optical elements are added at this stage. And of course, we like to have a control system. So we need to control altogether this object. And nowadays, all these steps are separated. that they even can be done in separate plants, separate fabrics, and only after that they put together in one place. But the idea is to have integrated solution. So with the help of this integrated solution, it will be possible to reduce the cost. And this idea is illustrated here. If we have inside such lamp nowadays a very complicated driver, so electric scheme which produce necessary stable current, and then we have numerous diodes, then everything should be substituted by the so-called integrated smart LED circuits. And this will be a similarity with the breakthrough transition which was in the 60s in electronics, when industry shifted from the single transistors to the integrated circuits. And everybody knows that, of course, in our cell phones, in our TV sets, we have all these integrated circuits. And the aim is to have such integrated circuits in case of LED devices. Good. So what K-target is for the nearest future? So nowadays we have such efficacy with the CRI of the order of 80 and 85, but in the nearest future we like to have efficacy about 200 lumen per watt, and the lumen cost, as I said, $2 per kilolumen. So when we reach these numbers, in this case, all luminescence lamp will be not necessary at all. Okay, but of course in this very nice economical picture, there are difficulties. Difficulties of two types: scientific difficulties and technological difficulties. So, what we have to do? Actually, for all these stages of production, we need to have advanced scientific solutions. In particular, first, heterostructures usually are made in this blue light emitting LEDs on the basis of 3 nitrides. So this is wide bandgap semiconductors, and necessary to design new type of the heterostructures with high quality, structural quality, and working at high electric currents. High electric current is required to make these devices smaller. In this way, we need to search for new materials with absolutely new electric, thermal, mechanical properties, both for the heterostructure itself, but also for holders. And here the transparent material are required, new phosphor materials are required, and so on. And in particular, new substrate materials are required, because nowadays all this industry works on the sapphire templates, sapphire substrates, or silicon carbide templates. But these silicon carbide templates are actually explored only by one company in the world. This is Cree, a very famous US company which uses the silicon carbide, high quality silicon carbide substrates for LEDs. Of course, such questions like thermal management is important. Still, the power of devices is very small. Let's see what is written here. This is probably like 6 watt device only. But because of this Stokes effect, the material is heated, and this heat influences very strongly on the parameters of the devices. Therefore, good materials for heat sinks should be applied. Then, which is of course is very close to the subject of our today's seminar, the light extraction from the chip, from the device itself, should be controlled and improved. This is a big challenge, and I see how it can be solved. And of course, all these features, including, for example, CRI index, should be applied for the integrated solution, not only for the single LED, but also for integrated solution. For example, why there is a problem with the electric current? From the first point of view, it seems that if we just put additional electric current, we have more electrons and holes in our system, and they will recombine and produce light. And therefore, if the density of the current grows, it will be more and more light. Yes, it is, and the curve shows this. But this dependence is not linear. So it becomes non-linear, and this is well-known droop effect, that we have the external quantum efficiency droop with the current. It is necessary to understand what is the reason for this droop effect and reduce. And here the table, no, I don't know, I don't have now time to go into details in this table, but it demonstrates what happened with the internal quantum efficiency, external quantum efficiency nowadays, and what is expected, and depending on the wavelengths emitted by LED. And the droop effect. Nowadays is 70%, and it is expected that when we can get out of this effect, we will have this 100% possibility to use very high density current, and therefore to go to very small LED devices. And of course, thermal stability is here. And the main reason for this droop effect, and now I already moved to the physical part of the talk, is the presence of various types of defects in the material what is used. These defects are dislocations, so-called threading dislocations, the typical gallium nitride layer grown with the metal organic chemical vapor deposition, and MBE, either MBE on the sapphire structure of this gallium nitride layer shown here. And we can see a lot of these dark lines with very high density. Density is 10 power 9 centimeter per square centimeter, which is extremely high. And these dislocations, they are very bad for carrier transport, for optoelectronic properties, and for optical properties. Therefore, there is a challenge to reduce the density of this threading dislocation. And this can be achieved by various methods. One of the methods is demonstrated here. So the researchers, they try to modify the growth technology. For example, when we change the growth mode of these layers from the island growth to the layer by layer growth, we can add to reaction between among dislocation in this layer, and therefore the density of this dislocation can be reduced. And this is shown here. Then, applying such sort of techniques, we can reduce dislocation density, maybe half order of magnitude, or maybe in order of magnitude. And namely, this effect was used at Optical company to get rather good results with the LEDs. The other possibility is to change the construction of the light emitting chip. Here is shown the traditional so-called standard horizontal LED structure, when the current goes horizontally through the chip and different elements are demonstrated. It is proposed to change the structure to the vertical geometry, where the current can go from the top to the bottom. And in this case, the current will spread rather uniformly, and the working zone of the device where this heterostructure is sitting will be therefore loaded more uniformly. And of course, other thing which is also given in this figure is the use of different type of the substrate. Instead, using the sapphire substrate, it is possible to use homo substrate, so-called homo substrate, gallium nitride substrate, which will be good for blue LEDs. Then it is, in principle, it is expected to apply gallium oxide, which is quite new material, and I will talk about this very soon, for UV LEDs, and also use so-called non-polar oriented substrate for the green LEDs. Therefore, use of different substrate material is very perspective and promising. And here, of course, there is a challenge to get such big wafers of gallium nitride. Gallium nitride is material which does not grow at the atmospheric pressure in liquid phase. So it can grow only at very high pressures from liquid phase. And therefore, such technologies which are usually used for silicon and other type of materials, they cannot be applied here. Yeah, and therefore it is extremely difficult to get such wafers of the gallium nitride to substitute sapphire wafers. And I can tell you that nowadays the price of the maybe 2-inch wafer is about $1,000 for gallium nitride. When you compare it with sapphire, where it is maybe $20 or less, you see the big difference in the price. But still, it was demonstrated if such templates, such wafers are used, it is possible to achieve a record efficacy for the blue LED devices. So here it is written that 200 lumen per watt was achieved for such type of materials. Then, of course, it is necessary to try to develop alternative techniques, and here you see that one was obtained by liquid phase epitaxial growth, and it means that a very complicated, high pressure, high temperature, very dangerous devices were used, and it's necessary to search for other methods for getting for production of such type of substrate. And one of these methods use the nano imprint on nano lithography, where we form the row of columns somehow during the growth of the gallium nitride layer. In this case, internal stresses will be not transferred from the substrate to the top layer, and even more, the presence of such columns can be used for self-separation of the gallium nitride grown layer grown by, for example, HVPE techniques. This is chloride gidride vapor phase epitaxy. And then it is possible to use these templates to form already LED structures and make LED chip. This is three-dimensional picture of typical LED chip with the substrate which has these nanocolumns or micron holes or cavities. Also, the presence of such cavities will help to extract more light from this structure. And here I have the experimental data for the LED chips grown on such patterned template. And it's possible to see, in this case, some increase in the efficacy. Not so big as we have expected, but still 15–20 additional % of light can be extracted from these structures. Still, droop effect is here, not disappeared. A few words about this gallium oxide material. This is brand new direction, just generated maybe 2 years or 1 year ago, and the direction is on the possibility to use gallium oxide for various optoelectronic applications. Gallium oxide is a wide band gap semiconductor with the remarkable properties, rather high electron mobility, but what is important, with very high breakdown field. The breakdown field is, electric field is somehow very close to those for diamond. Therefore, it is expected that the use of this gallium oxide material will also help a lot in the LED-related problems. And I report now that at Yoff Institute and also in the cooperation with our LED chair at ITMO, we already succeeded in the getting first balls of this gallium oxide using the liquid phase processes. To the contrary of the gallium nitride, this material can be processed using the liquid phase. So it is a big advantage. Okay, I just go very fast through the two other challenges. One is the thermal management. As I already mentioned, thermal management is extremely important for LEDs. And we at our department and researchers through the world, they spend a lot of time trying to make trying to keep LED structures at low temperatures. We have heard today already a lot about the desire to control temperature in optical system. The same is here. Of course, here maybe not so big accuracy is required, but still we need to keep LED operating, say, at temperature not higher than 60 degrees centigrade. If it goes to 100 degrees, the efficacy goes down. And other important question is the light extraction using the primary optics, which can be directly built on the LED chips, and secondary optics. And here, of course, all these methods developed in the community, which I see here today in the room. Of course, they will be and they are very useful for the analysis of LEDs. And here is an example how we try to optimize the shape of the small lenses on the top of the chip-on-board LED model. And here optimization permitted us to predict the desirable shape, and then it was possible to order the mold with the specific shape for such devices. Okay, so now I try to talk about the technological challenges. Of course, they are numerous, many of them. And first, it is necessary to have a transfer from the scientific achievement to the technology. And here, I will tell you rather obvious things, that in this case, it is necessary to correctly work with the intellectual property. So today, so I have heard a number of talks, and only I believe maybe one or two I have heard about this intellectual property. But nowadays, this question is extremely important and extremely useful, and we, together with Optical, try to follow this general world tendency, and here is the example of our activity. And I think that this part, together with the scientific, technological sense, economical, is also extremely important for all this lighting industry. So, technological and engineering challenges. First, I give the example how this process developed at Optical. During the last say 3 years. Optical started operation in Russia 2010, and therefore you can see the change of the efficacy of the diodes, which now reach 160 lumen per watt, and also drop in the price, the dollar per kilowatt. And here also the parameters of the devices, of the luminaries, which are produced by Optical, including office lighting, which is the main product, and other type of lighting. Everywhere we see the increase. So this is the general tendency in such type of companies and in the world. To see what type of the challenges we have, I like to consider the example of the same bulb, and I will give it again once more later. So what they are? First technological challenge is, of course, the growth of these heterostructures or growth of the substrate. Therefore, it means that a very complicated equipment is required. A lot of management of this equipment is necessary. So altogether, it is a rather big problem. Then, when we go inside such a bulb, we will see that if we like to have integrated solution, so therefore, in this case, we need to integrate our light components, light emitting components with electronic components. And electronic components nowadays, they are mainly silicon-based. Therefore, we like to have the integrations with silicon technology. Therefore, these gallium nitride layers or other material layers should be grown on the silicon. And it itself is rather complicated scientific and technological problem too. Okay, then I have here the challenge to go from single elements to modules. Therefore, we expect that these elements will be on single board sitting, and we will have so-called chip-on-board solutions. And for these chip-on-board solutions, phosphors also should be incorporated for the whole board. In addition, we need to upgrade the power supply from these huge supplies which use the big capacitors. New suppliers with small capacitors are required. And here, of course, for these capacitors, we expect to have new materials. Therefore, transition to the principally new materials is again a big technological challenge. We of course know that if we try to just substitute one material by the other, even this new material has a much better properties. So in this case, it is technologically is not very easy, even if scientifically it is already proved that there is advances. Now I give 3 examples for these technological challenges, and one example repeated a third time is this retrofit bulb. So there is a challenge, actually technological, to get the chip on boards inside with such parameters. CRI is larger than 80, and the light temperature is more than, say, 3000 Kelvin, and the efficacy more than 160 lumen per watt. Currently, I believe that this one will be about maybe 120 lumen per watt. And to solve this problem on the sapphire substrate is practically not possible, but now some foreign companies, some big companies like Philips, they announced that they move to the gallium nitride substrate in this commercial product. Not only in the research product, but also commercial product. And here is the aim, what should be in such bulb. is about 5,800 Kelvin temperature, light temperature. The spectrum from 400 to 700 nanometers, and the 250 per watt. Example 2, light control system. I did not tell much before about this control system, but it is absolutely clear that the use of solid-state lighting gives us the very good possibility to have control system integrated together with electronic and lighting system. And what is now standard components? Of course, we all know the switcher, which we have, but still the switcher should be integrated inside together with more advanced things, control module, drivers, sensors. So our devices, they should have so-called digital assembled lighting interface. So it will do switch off, on, required brightness, dimming, group control, and even more, this should be done through the network. And altogether, this will be this integrated lighting integrated circuit. In particular, this will have importance for greenhouses in agriculture, where the light is required of special quality and also together with controlled structures. And our chair is also somehow involved in the development of such products for agriculture. And finally, the last example, this chip-on-board solutions. I like to demonstrate the solution which already exists, but the idea of this chip-on-board solution is shown here, that we have a common board, and this on board we put chips, and for these chips we have joint electric connectors, and then all together we cover this with the phosphor. And such type of system was realized by Optical in a very good product, which is known like, like X10 modules. So you have a such plate with all electric contacts inside and connections, covered by the phosphor, which then this plate can be separated into modules by simple mechanical loading. Therefore, you may have LED modules with given power. So, and after that, you can use these modules like in Lego constructor, put in your device what you like, and all electric connectors are inside. And nowadays, we are working on the additional optics for such modules, but this optics should be cheap. So this is the problem. This is not optics like for telescopes. And of course, there is a room for further development of such type of products. For example, for these LED modules, patterning of the interface can improve light extraction. Then secondary optics, diffusors and so on can be included and calculated and modeled and then used in practice. So-called remote phosphor decision solution can be proposed to reduce these temperature effects. Of course, reflectors also can be added to these devices, and of course it is necessary to compute optimal shape and properties of such reflectors. And for sure it is necessary to have the thermal management of all these components. Therefore, this mix of this ZMAX and other type of FEM programs is of course welcome to use. Okay. And in conclusion, I like to tell you that I try to present the mix of economy issues, economical issues, scientific issues, and technological issues. And for LED industry, only altogether this can work. This is not possible to do this separately. And finally, thank you very much for your attention.
Совершенно неожиданно безмерный доклад о мире светодиодов. Мы услышали. Спасибо большое. Вопросы?
Oh, thank you very much for that really interesting talk. I have two questions. Could you tell me of a success ratio of working diodes because you are manufacturing diodes, right? On a wafer. So what's the success ratio? How many of the devices actually work?
Output.
Yeah. What's the...
Okay, so I actually can tell you that I was the chief of scientific department at Optical. Therefore, the success ratio is not my task. If you will visit Optical, you will see that when you organize the process correctly, the ratio what they have is 97%.
Wow. Okay.
Yeah, it's extremely high. And you will see if they will show you this tables list. They check this every day, put the devices, and then follow, get back. And what I can tell you in connection is all problems what can be with such type of devices. They not are related to LEDs. They are related to the drivers and to the mechanical contacts, like a soldering, for example. And if there is some defect, usually it is there. LEDs never fail. Yeah.
Okay, thank you. And the other question, could you comment please on the different type of diodes, I mean the organic diodes, because you were talking about GaN. Would you comment if the organic is a future or
it depends.
Can be competitive to LEDs?
Okay, so this is a very good question, and of course we try to follow all tendencies, all trends in this solid state lighting, including organic lighting. Even more, we have a subdivision at Optical, organic lighting solution. So the aim was for this subdivision was to see if it really nowadays possible to have competitors for such efficiency. The answer is not. It's not possible. But they have other additional features which are important. For example, with the help of these organic diodes, you can make a display which
Panels,
you can bend.
flexible.
Yeah, flexible.
Exactly.
So this is good. Then you can use it at many design features. For example, columns or some parts of your
ceiling
can be easily covered with this organic. But still, efficacy is rather low. Okay. So nowadays it is about, I believe, 50 lumen per watt, and this is a record nowadays. But also the other thing that environment, how they are will stay in this dangerous environment. So therefore, in many cases, this organic stuff should be covered after that by glass, which also additional losses, and then this not becomes flexible. Therefore, yeah, question. But still, this is good because good direction. A lot of research is so it develops.
Okay. Thank you.
Еще вопросы?